Let's talk about quantum mechanics. I know. The word itself can sound, well, pretty intimidating. It brings up ideas of a bizarre, hidden world with rules that are completely different from our own. But what if we had a key, a kind of Rosetta Stone to help us translate its strange and incredibly powerful language? Well, that's what we're going to do here. We're going to use our source material to decode the fundamentals of the quantum world.
So where do we even start? Let's begin by building a bridge from the world we know to the one we want to understand. We all live in a world of classical computers, right? Your phone, your laptop, they're all powered by a very simple idea, the bit. To get a handle on the next massive leap in computing, we first need to meet its quantum cousin, the qubit.
So what's the big deal? What's the difference? Well, a classical bit is straightforward. It's decisive. It's either off or on, a 0 or a 1. That's it. But a qubit is, as our source material perfectly puts it, slippery. Thanks to a wild property called superposition, a qubit can be a 0, it can be a 1, or, and this is the part that changes everything, it can be both at the exact same time. This one single difference is the entire foundation for the power of quantum computing.
Okay, let's get the formal textbook definition out of the way for a second. It sounds complicated, I'll give you that. But really, all this means is that a qubit is a system with two fundamental states. We can just call them 0 and 1. The real magic, the secret sauce, comes from all the possible combinations, that superposition, that can exist between those two anchor points.
All right, so that's the theory, but it can feel a little abstract, right? You're probably asking, okay, but what does being in two states at once actually look like? Let's ground this with a brilliant and surprisingly simple real-world example.
Take a look at this. It's a photon, a single particle of light, and its polarization is a perfect physical stand-in for a qubit. You know how polarized sunglasses work, right? They filter out light that's vibrating in a certain direction. So we can just decide to label light that's polarized horizontally as our 0 state and vertically polarized light as our 1 state. But here's the thing. A single photon can also be in a diagonal state, which is a perfect 50-50 superposition of both horizontal and vertical at the same time. It isn't one or the other. It's literally both.
Okay, so we've met the qubit. Now we need to learn how to speak its language and, maybe more importantly, get a feel for the incredibly strange rules of its world. This is where our Rosetta Stone really comes in handy.
So the language physicists use to write all this down is called Dirac notation. When you see these symbols, the vertical bar and the angle bracket, that's something they call a ket. Don't let it intimidate you. It's really just a label. Think of it as a fancy way of writing the quantum state of our system. Whether that system is our photon's polarization or something else. It's basically the noun in this new language.
And here we have it. This is the most important, the most mind-bending rule of the quantum game, straight from one of its founding fathers. And it says that in the quantum world, you can't just be a passive bystander. The very act of measuring something forces that system to jump, to pick a side, to snap out of its superposition and choose a single definite state.
Now, I know what you're thinking. That sounds completely nuts. How can just looking at something change what it is? It sounds more like philosophy or science fiction than hard science, but it is a demonstrable fact. Let's actually see it in action with a really cool experiment.
Okay, follow this closely. You take a filter that only lets vertical light through, and you put it in front of a filter that only lets horizontal light through. You put them together, and nothing. No light gets through. Total darkness, exactly as you'd expect. But now, you do something that seems like it shouldn't work. You slip a third filter, one that's polarized diagonally at 45 degrees, right in between the first two. And suddenly, some light gets through the whole thing. How on earth is that possible? Well, that middle filter acts as a measurement. It forces the photons into a new diagonal state. And because they are now diagonal, some of them have a horizontal component, which allows them to sneak through that final filter.
And this is the whole point. That diagonal filter didn't just passively watch the photons go by. It actively participated. It forced them to answer the question, hey, are you diagonal? And by the very act of answering, they became diagonal. In the quantum world, observation isn't a passive act. It's an interaction that fundamentally changes reality.
And what's really interesting is that there isn't just one single way to describe this bizarre reality. Physicists have different mathematical models, like the Schrödinger picture and the Heisenberg picture. On paper, they look totally different. In one, the states move, and in the other, the measurements move. But they're like two different languages describing the exact same event. They are mathematically equivalent, and they give you the exact same correct predictions. It just depends on the perspective you want to take.
All right, now we're ready to tackle the big one. The most famous, the most hotly debated, and maybe the most powerful and bizarre concept in all of quantum mechanics: entanglement. This concept is so strange, so seemingly impossible, that it famously bothered the heck out of Albert Einstein. He just couldn't bring himself to accept it, and he thought it was a sign that the whole theory was missing something. He's the one who gave it its famous nickname, spooky action at a distance. So what is this spooky action? Well, entanglement is what happens when two particles become linked into a single quantum state. In a way, they kind of lose their individual identities. They become one unified system. And the truly weird part is that this connection sticks around no matter how far apart they get. What happens to one of them instantly affects the other one, whether they're a millimeter apart or on opposite sides of the galaxy.
So back in 1935, Einstein and two of his colleagues basically threw down a challenge. They published what we now call the EPR paradox, and in it they argued that entanglement just had to be impossible because it seemed to break the most fundamental rules of the universe as we knew them.
And their objections made a lot of sense. First, how could this influence happen with no force connecting the particles? There's no string, no gravity, nothing. Second, the effect is instantaneous. That seems to shatter the ultimate speed limit of the universe, the speed of light. And third, unlike every single other force we know, the strength of this connection doesn't get weaker with distance. It was all just too spooky to be true.
But here's the incredible twist in the story. Einstein was wrong. For decades, physicists have run increasingly precise and mind-boggling experiments, and they have confirmed quantum mechanics at every single turn. They've proven beyond any reasonable doubt that this spooky, instantaneous, distance-defying connection isn't a mistake. It's a real and fundamental feature of our universe.
So, we have superposition. We have measurements that change reality. We have spooky entanglement. This is all very cool, very mind-bending stuff. But why does it actually matter? Because when you learn how to harness these bizarre ideas, you unlock a completely new era of technology, quantum computing.
Let's go back to that idea of superposition. A classical computer, like the one in your phone, with 3 bits, can hold just one number at a time. Say the number 5. That's it. But a quantum computer with 3 quantum qubits can hold every single number from 0 to 7 simultaneously, all at once, held in that superposition. This isn't just a small upgrade, it's a totally different way of processing information, something called massive parallelism.
And this power, this ability to explore a huge landscape of possible solutions all at once, is what will allow quantum computers to solve certain problems that are practically impossible for any classical computer we could ever build. We're talking about things like discovering new medicines, designing revolutionary new materials, or breaking incredibly complex cryptographic codes. These are the kinds of world-changing problems quantum computing is set to tackle.
The quantum world also has its own unique rules about information itself, and one of the most important is something called the No-Cloning Theorem. In our classical world, we copy information constantly. It's the foundation of the digital age. But in the quantum world, it is physically impossible to create a perfect independent copy of an unknown quantum state. You just can't do it. And that has huge implications for things like secure communication.
So, when you boil it all down, what's the crucial point? Understanding all this weirdness, superposition, measurement, entanglement, it isn't just a fun thought experiment for physicists. It is like we are learning the grammar and vocabulary of a completely new physical language. And by speaking that language, we are starting to build an almost unimaginably powerful new kind of machine.
And that leaves us with one last really provocative thought. For centuries, we thought we had a pretty good handle on the rules of reality. But quantum mechanics has shown us there's this deeper, stranger, more fundamental layer underneath it all. So, if a particle can be in multiple places at once, and 2 particles can be linked instantly across galaxies, it really makes you wonder, doesn't it? What other fundamental rules of our reality are just waiting to be rewritten?